So let's move on to the last talk of this session, and this is from Ron Creel, who's bringing his expertise and history to the Apollo Dust Lessons Learned for Artemis. And,
Good afternoon. Can you hear me?
yeah, we can see you and hear you.
Okay, very good. The title of the presentation, as they said, is Apollo Dust Lessons Learned for Artemis. The subtitle is Let's Keep Lunar Dust Outside and Greatly Increase Science Time. I would like to point out that in the agenda, the name of Dr. Bonnie Dunbar was left off. Bonnie is a former astronaut who's flown 5 times in space, and she's been a very important part of our compilation of this presentation. You see a picture of Apollo 15 rover sitting on the moon. I could tell that's Apollo 15 because the left front fender extension is missing. And that didn't cause a problem on Apollo 15. It also, the dust covers are open, which the astronauts did after each driving period. And this is the way it looks now, and it's been looking this way for 50 years. I would like to point out one thing. We did not use slide rules. We used computers. In fact, I did constant battle during Apollo 15 with the NASTRAN structural program that was running on the UNIVAC 1108. And we got priority, and we did get our runs done on Apollo 15. Then I developed a simpler mission support program for Apollo 16, and I did receive the Silver Snoopy for that. Let's go on to the next chart. There are 5 lessons we're going to go over. Lesson 1 is ever-present hazardous dust cannot be avoided on the moon. Lunar dust proved to be a significant and potentially dangerous hazard on previous Apollo moon missions with short crew exposure times. Lunar dust was easily stirred up and deposited on crew suits, rovers, and science equipment during EVAs, and then brought on suits into the lunar module habitat. Shown mechanisms here, several different ones: driving, walking and falling, sampling, even kicking up dust onto the Apollo lunar surface experiment packages. And then certainly on both Apollo 16 and 17, the commander had a hammer in his suit, which caught the edge of the fender extension on the right rear fender and popped it off. This happened early in Apollo 16, and there was not time to make a fix. However, on Apollo 17, they did go back in and figure out that they could use lunar maps, use duct tape to piece them together, and use clamps from the lunar module to clamp on this fix. Increased thermal radiator solar absorbance, alpha sub S, resulted in reduced battery and communication equipment cooldowns, which necessitated replanned cover openings, battery switching, and an overtemp on the surface electrical properties experiment, the SEP science experiment. Lunar dust behavior at new proposed moon exploration sites is unknown, i.e. the poles and PSRs. But early indications today say that the lunar soil should be about the same at these other locations. Lesson 2, next chart please, sir. Lesson 2, valuable science time was wasted in fruitless housekeeping. Misleading pre-Apollo 15 Earth testing at the Manned Spacecraft Center, even using Apollo 12 soil, showed that brushing could be used on the moon to effectively clean thermal control surfaces and crew suits. Here's a picture showing an astronaut using a dust brush to clean off the radiators. But you can see from the plots here taken from the Flight Evaluation Working Group report, on Apollo 15, we started to see after the second cool down period that we weren't getting any cool down because the dust was not adequately brushed off and cleaned. In summary, extensive dust cleaning regrettably did not work on the moon. It did not work. Next chart. Lesson 3. We must listen to the right persons about dust problems and solutions. The Apollo crew mission report observed some type of throwaway overgarment for use on the lunar surface may be necessary. We did not pay attention to that, and it came to roost on us later. I asked Charlie Duke to give me a summary on Apollo 16. You see Apollo 12, 16, and 17 located on the picture on the right. On Apollo 16, we had brought a lot of lunar dust into the lunar module. When we got into orbit, all the dust floated all over the cabin. It was so bad we were concerned about our environmental control system, so we stayed buttoned up in our suits. After we docked, Mattingly would not let us come into the command module. He floated over a vacuum cleaner and closed the hatch until we got most of the dust vacuumed up. In summary, for long lunar stays with multiple EVAs, I believe an airlock would be mandatory. You've seen pictures, I think, before of Commander Cernan on Apollo 17 sitting in the lunar module, frustrated and tired with the dust covering his suit. And he had trouble even getting the helmet dislodged and unscrewed. He said, "I think dust is probably one of our greatest inhibitors to a nominal operation on the moon. I think we can overcome other physiological or physical or mechanical problems except dust." He also commented later that due to dust problems, a fourth EVA would not have been possible. I've since found out that on the trip back to the lunar module on the third EVA, the gate, the swinging gate back there that held its tools in place on the aft pallet was not able to be closed. It flung open and we lost some tools. So certainly a fourth EVA was not possible. Let's go on to the next chart, please. Lesson 4. We must pay attention to alarming lunar dust toxicity test results. NASA has sponsored research which shows evolving opinions about the potential for lung damage from ingested lunar dust. Apollo astronauts, as Jack Schmidt noted this morning, did note some irritations and allergic reactions for their showed exposure times. In 2014, a group called the LADTAC, Lunar Airborne Dust Toxicity Assessment Group, reported minor concern for postulated safe exposure estimates, Cs. This was based on animal testing here on Earth with long-term stored Apollo 14 soil. Recently, I was very concerned to see in July of this year some new reports presented at the NASA Exploration Science Forum and European Lunar Symposium. The new toxicity reactivity testing results were presented. They showed that alarming toxic effects with significant potential for lungs and other organ damage from ingesting simulated lunar dust. Submicron dust can be absorbed into the circulatory and nervous systems. Their summary was there will be nuclear and mitochondrial DNA mutations, which may cause mitochondrial dysfunction. It's also inevitable to lead to tissue damage or even cancer, especially in lungs, when the astronauts breathe in the dust attached to their spacesuits. This diagram shows you the process from exploring, disturbing the dust, getting it into the lungs, and then the mutations that can occur later on. We cannot afford to wait for additional Earth or moon dust testing for Artemis crew's help. Next chart. Lesson 5. We must do everything possible to keep dust out of habitats and lungs. Having crews and suits not be directly exposed to dust in the first place is the best way to survive adverse and hazardous lunar dust effects, as is done on Earth with protective overgarments. We show examples here of suit covers and hang-up areas, as well as suit cover donning and doffing. NASA, even back in 2007, did special spacesuit cover don and doffing tests, which showed that you could do it in less than 10 minutes. NASA has designed and tested isolation technologies that can help ensure good astronaut health and increase Artemis science time by leaving the dust outside the lunar habitat and explorer lungs. Lightweight, flexible, and reusable suit covers for astronaut suits and the suit joints protection with airlocks and suit ports for future Artemis EVAs, rovers, and lunar bases are needed. I show here some examples of a patent done at NASA Ames back in 1989, showing the airlock with a suit port attachment where the astronaut gets into the suit from the inside of the airlock and then explores and comes back out. When I went out to Johnson Space Center in 2007, they invited me out there to talk about our rover experiences. They showed me the Chariot rover. And by the way, the Chariot rover was in the 2008 presidential inauguration parade. This was amazing to me that somebody had thought out here not only to have airlocks, but to have suits that attach to the back of the rover so that you could leave the suits outside. The drawing on the right there shows something I mentioned a little bit earlier today. It shows an area with a grating in the bottom so that you could actually dust off your feet, and before you went into the airlock, after you hung the suit up, and you go into the airlock. These are concepts that I think should be pursued. Let's go on to the next chart. This is the final chart. I think that our team thinks that we are at a dust crossroads for Artemis. Let's not repeat the Apollo lessons. On the chart, the diagram below, I show on the horizontal axis there, dust removal equipment testing, both on Earth and on the moon. On the left side, Earth-based moon dust environment simulation and testing is very difficult and not reliable, as we showed before Apollo 15. This is because of limited low gravity and low pressure testing capability. On the right side, if we wait and try to do this on the moon, we endanger the early exploration crews by waiting for moon dust environment testing, and which will again exhibit considerable wasted science time. The answer, as you proceed up arrow on the path, the crossroad going up to the top, is isolation technologies. We need to take action. We need to implement suit covers, airlocks, and suit ports to ensure good astronaut health and maximize science time while minimizing housekeeping time. This process may also include masks with filters for use inside the habitat. I want to show y'all, and it's going off the stage chart, that what happens if we don't do it, if we stay the course and we don't take action. We're going to repeat the toxic hazard, and we're going to waste even more science time. I have calculated here, we're going to show a 2-minute video showing a frustrating effort by the Apollo 16 crew to clean their suits with housekeeping. And we saw earlier in the presentation that they still brought lunar dust into the habitat, which was a problem. So can we show the video now? This is off the color TV camera on the rover.
I think you've got a lot of it on you too. No, it's okay. Looks like you guys have been playing in a cold bin. Yeah, well, I'm not sure we want all this stuff to get up there in that machine with us. I don't know how we'll get it all. Let's do the best we can. Yeah. Let me have it, John. Okay. I promise not to. Oh, your pocket's pretty good, John. Take a little while. Okay, let me get under here. I tell you, Houston, my general impression of this thing is I'm a lot more surprised at how really beat up this place is. It must be the oldest stuff around because it's just craters on top of craters on top of craters. I mean, there's some really big old subdued craters that we don't even have mapped on our photo map, I'm sure. Bend over, John. So they just show up as general depression. Okay, that's good as I can do. Okay, we copy that. There you go. Okay. Okay. Tony, one of those big rock bags those big rocks I could put into the SRC. It's an undocumented rock grab sample. I don't mean the SRC, but the SCB.
Okay, that's about the end of it.
Get it for next time, Tony.
Thank you, Kevin. That's about the end of it. That summarizes it for me that we've got to do something here to help protect the astronauts, ensure their good health, and also to minimize the science time. We wasted an awful lot of time. As I calculated, that 2-minute video that you looked at, that's equivalent to $82 million of the Apollo program costs.
Thanks, Ron. Thanks for bringing that video along and sharing that. I like the paintbrush approach to cleaning that stuff too.
It worked here on Earth, but it did not work on the moon.
We just need to work on a better paintbrush then. Okay, well, this has been a really fascinating session. I want to thank all the speakers